This presentation is on measurements and significant figures. So the beginning part we've already talked about in class on Friday, accuracy and precision. The second half of the presentation, again, is on measurements. So we've learned about significant figures and calculation, but now we're also going to learn how to make measurements using the correct number of significant figures. So again, beginning with what we talked about in class on Friday, accuracy and precision. So as a refresher, accuracy is a measure of how close a measurement comes to the actual or true value of whatever is measured. Okay, so how close the answer or how close a measurement is to the correct answer or the correct measurement. Precision is a little bit different, and it's a measure of how close a series of measurements are to one another. So nothing to do with actually being correct, but just how close the measurements are to the other measurements that you've made. So here we have three dartboards that kind of show us the comparison between precision and accuracy. So here we have three darts close to the bullseye and close to each other, making it both accurate and precise. So this is our goal. Obviously, we want our measurements to be close to the correct answer or the correct answer, and then we want them to be precise because that means that those values were close together and multiple times you were close to the correct answer. All right, for letter B, we have darts that are off to the side here. They're close to each other, but they're not close to the bullseye. Because they're close to each other, this makes them precise. Because they're not close to the bullseye, they are not accurate. Right, and then the last dartboard shows three darts separated. Neither of them are close to the bullseye, so they're not precise and not accurate. This is a synopsis of the previous slide with the dartboards. So to evaluate the accuracy of a measurement, we have to compare the measured value to the correct value. So again, we compare the measured value to the correct value. Closeness to the bullseye on the dartboards was the measure of accuracy. So the closer to the bullseye, the more accurately the dart was thrown. Again, precision is something different. Precision, we are comparing our values that we've measured to each other. The clustering of several darts together is precision. Again, a reproducible amount. So precision can be thought of as reproducibility. All right, so on Tuesday, when we get back to school, we are going to calculate error. You used the density lab to figure out the densities of two unknown metals. And on Tuesday in class, I'll give you guys the true values for the densities of those metals. You're going to use that to calculate error, or how far off you were from the true answer. Okay, so we're going to make measurements in this lab, and you guys already did, that require us to think about the accuracy of the measurement. Anytime that you measure values or you're doing a lab, they're called experimental values. So you have two calculated densities of metals. Those are your experimental values. We're going to compare those values to the accepted value or the true value of the density of those metals. So it's called an accepted value or the true value because it's been measured so many times that now we can find it in reliable sources. So I'd mentioned those data tables showing densities of different objects and how scientists can use those to identify different materials. Those are accepted values. They've been tested over and over again, and every single time those values hold true. So that's what we're going to use to determine how much error you had in your lab. There is a formula for calculating error, and it's listed here on the screen. So we have the experimental value minus the accepted value. All right, again, experimental value is what you guys got in the lab, so lab measurements. And then the accepted value is this like table value or true value. True/correct value. So you want to find the difference in your experimental and accepted values. Notice how we have these absolute value signs here. That just means we're not going to have a negative number on top ever. Okay, so experimental value minus our accepted value, then we divide it by the correct value, accepted value again, and multiply it by 100. All right, so again, it says note the absolute value around the numerator. This means that percent error will always be a positive value. So for percent error, we are looking for values that are as close to 0 as possible. So if this value is close to 0%, 0% error, this is ideal. That's what we want, okay? We don't want any error, which inevitably does happen, but the closer to 0 that the value is, the better this is. Okay, so if this value is close to 0% error, this is good. Okay, it means that we didn't have a lot of error in our experiment. The closer you are to 100, the worse off your calculation or measurement was. Okay, so we want this value to remain as low as possible. All right, so we're going to do an example where we're calculating the percent error. So it says that I've measured the boiling point of water. On that thermometer, the boiling point of water was measured to be about 93.5 degrees Celsius. The accepted boiling point of water in Denver is 95 degrees Celsius. Okay, so this 93.5 is what I ended up measuring. This is my experimental value. And then they told us that the accepted value, or the correct or true value, is 95 degrees. So accepted. All right, so now we want to calculate the percent error. So I'm just going to go ahead and plug these numbers into the previous equation. Experimental minus accepted over accepted times 100. So I'm going to write that here so I don't forget it. Equals experimental minus accepted over accepted times 100. All right, remember, this top portion of subtraction does have absolute value signs. So let's plug our numbers in. Experimental 93.5 degrees minus 95 over our 95 degrees times 100. All right, math-wise, when you do this, you always want to subtract the top numbers first and get your answer. So when I take 93.5 and subtract 95, obviously I do get a negative number. So this is actually negative 1.5. But we have absolute value signs here. So I'm just going to write the answer to that part right above here, which is 1.5, making it positive, again, because of those absolute value signs. So I'll do 1.5 divided by 95, and then multiply by 100. The answer that I end up getting is about 1.58% error. All right, so these are kind of the units for percent error. You always want to make sure that you have some sort of a label, not just the number. So this is a very low percent error. Again, the closer to 0, the better the calculation or better the measurement. Okay, so this isn't too bad. All right, so now sig figs with measurement. So we've learned how to round answers for addition, subtraction, multiplication, division, but there are also significant figures when you make your measurements. So when we measure something, we can and do always estimate between the smallest marks. Okay, so we can see that we were measuring this like little teal strip here, I don't know, whatever it is, and we have our ruler on the bottom. Okay, so we know whatever this measurement is, let's say it's centimeters, I don't know. Let's say that we know for sure that it's over 4 centimeters, but it's not 5 centimeters. So we do estimate. Okay, so you might look at this and say it's 4.5 or 4.6. Okay, so that second number, that 0.5 or 0.6, is our estimated digit. The 4, everyone should have the same. We can tell that it's over 4, and we can definitely tell that it's under 5. But that decimal place would be our estimated digit. All right, so the ruler, in this case, has changed a little bit. So let's say, again, this is still centimeters, all right, but now I've added more marks. On the previous slide, it only had marks between each centimeter. Here, I have a mark every single like 0.1 of a centimeter. So this is just showing us the better that the marks are, or the more markings that there are on a piece of equipment, the better we can estimate. All right, so it's always understood that the last number in a measurement is the estimated digit. All right, so here in this ruler, I can tell, okay, well, it's still over 4 and under 5. It's actually over, here's 0.1, 0.2, 0.3, 0.4, 0.5, and here's 0.6. I can tell that it's between these two numbers. So I know definitely that 4.5 are the first few numbers of the measurement. This would be my estimated digit. So I can see that it's about halfway between 0.5 and 0.6, so maybe the measurement is 4.55 centimeters. All right, and again, this last number, or whatever number we estimate, we know that that's the estimated digit because it's the last number we write, okay? So again, scientists always understand that the last number measured is actually an estimate. All right, so again, taking a look at some different examples here. If this was a centimeter scale, so this is showing us like a ruler on a centimeter scale, we can tell that the measurement is definitely 9 over 9. Okay, so we know the 9, and the estimated digit here is that 0.8. Okay, so we're thinking it's, a little more than half, so maybe it's 0.8. So this measurement, if it counted up by centimeters, then our estimated digit would be the 10th place. All right, let's say that this is kind of like a zoom in to that last centimeter, and there's millimeter markings. Okay, so millimeters indicated between centimeters. All right, so here's 9. So what this number actually means here is like 9.1, 9.2, and so on. For scale, we know for sure that we're past 8, and we can estimate this like 0.5 part right here. And then again, we know that this is within the range of 9, so it's 9.85 is our final measurement. This 5 is our estimated digit. Okay, I can tell that it's definitely past the 8, and I think it's about halfway between 8 and 9, which is where I got that 5 from. All right, so when we make measurements, again, we talked about how we're always going to make a measurement to one place past what the scale is incremented to. All right, so this is just a reminder for like what the placeholder names are called. If you ever get stuck on, hey, what do I round this measurement to? Just take a look at or write down this number, 10,000 with a few decimal places after it. All right, so anything that comes before the decimal, okay, so you know that this is the ones place, the number before that is the tens place, the hundreds place, thousands place, and then the 10,000s place. Behind the decimal, again, are smaller increments. The tenths place, hundredths place, thousandths place, and then 10,000ths place. Okay, so I'm going to write this number on every single one of the slides following just to show you guys what it means to make a measurement that's one place past what the scale is incremented to. All right, so if a scale is incremented to the tenths place, all right, so this is actually what you guys saw on your rulers. Every single centimeter, every single centimeter had 10 markings in between. That's the tenths place. So here's 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9, and then 10. All right, so every single one of these was tenth. This means that we estimate the next digit, which is the hundredths place. So technically, all of your measurements here should have included 2 decimal places. Okay, so when you were measuring the diameter of the rod and the height of the rod, you should have had 2 decimal places if you were using sig figs in measurement. Okay, so again, here's an example. We've got this pink bar, and the measurement is about here. And since we're on our iPad, we can zoom in. I know for sure that this is over 2.5. Okay, 2.5. And this is going to be my estimated digit. I don't think it's quite halfway. Maybe I'll erase what I drew so I can see where that line actually is. So I can estimate that this is 2.5 not halfway, so I'll put a 4 there, and then centimeters. Okay, so again, I could take a look at what this is incremented by. Each line is a 0.1, 0.2, 0.3. So each line is a tenth, which means I'm estimating this hundredths place. All right, if a scale is incremented to the tenths place, again, we should report it one place past to the hundredths place, like we just talked about. Okay, so again, 2.5, I estimated the 4 centimeters. All right, so this number, I said 4, and this says 4, but you could estimate that differently. Again, we know that the last number is an estimation. It's possible that you thought it was 2.53 or 2.52. That's okay, but you should really try to make an accurate estimation for that number. So if we had done this when we were measuring our diameters and our heights of the blue rods that you guys use for your density lab, it would have had a significant difference on your density calculation. Right now, if a scale is incremented to the thousands place, so let's say that we have this like massive graduated cylinder or something. We're going to use a ruler in this presentation because it's easier to picture. And it's incremented by the thousands place. So it counts by thousands, 1,000, 2,000, 3,000. If it counts by the thousands place, we always estimate the next digit. We're going to estimate the hundreds place. All right, so for example, here we have like this green thing we're measuring, this ruler, obviously not to scale, counts by thousands. All right, because it counts by thousands, the estimated digit will be our hundreds place. Okay, so our estimation here, the 2, we know for sure, it's past 2,000 centimeters. The 3 is the estimated digit. And again, this number could vary depending like from person to person. Someone else may have said 2,200 or 2,100, that's okay. All right, again, that second place or the last digit written is the estimated digit. All right, so the answers here are already given, but I want to go over why. So remember, you look at what the ruler is incremented by. If this is 1, this must be 0.5, half. This is counting by 0.1 every single time. All right, since it's counting by 0.1, 0.1 is written in the tenths place, which means I am estimating, again, I know this number, so I should be estimating to my hundredths place. So I should have 2 decimal places in my measurement, which we do. So again, 2.9 we know for sure, and then the 4 is our estimated digit because we think it's about halfway, but maybe not quite all the way halfway. All right, so this value here, okay, so this ruler is exactly the same. It counts by 0.1s. So this means, again, if I were to write down the number 10,000, I know this number for sure. Okay, I can see it's definitely like 0.9. I need to estimate that digit. Okay, is the next digit, the hundredths place. So I'm estimating the hundredths place. So I can see that it's barely past that line. So I could say 0.0 or 0.91 centimeters. Again, the last digit written is the estimated digit. Okay, taking a look at some more examples here. Okay, so we've got this teal bar. If I take a look at what this counts by, this is 10 millimeters right here. So that means that each line or each individual marking, remember that's how we base what our measurement's gonna look like, is counting by ones. So if I were to write 10,000, the ones place is right here. I should be estimating the tenths place. I should have 1 digit past the decimal. So if I take a look, right here is 20, 21, 22, 23, 24, 25. That's the number I know for certain. And again, we said we should be measuring or estimating our tenths place. So it looks like it's maybe about halfway, so 25.55 or millimeters. All right, so I said 0.55. again, this said here 0.3. It's okay because that last digit is understood to be estimated. If we take a look at our next ruler, again, what we want to look at is what it counts by. So if this measurement's 1,000, we know that this measure, or this like halfway point here, is 500. If it's 500, we know that each individual marking is 100. So let's write out 10,000 again. Oops, that's a decimal, 0, 0. We're counting by 100s, which would be this placeholder. I am estimating then my tens place. Okay, so if I take a look at my measurements, I know that this is 1,000, this is 1,500, 1,600, 700, 800, 900. So 1,900 I know for sure, and I know that I'm going to be estimating this digit. So it looks to be about halfway between 1,900 and 200. So I'll put a 5 there, and then I need that placeholder 0. All right, and then the unit, micrometers. All right, more measurements. We'll just go over what they count by. If this is 10, they're counting by ones, which means I am estimating my tenths place. Next ruler, okay, if this measurement's 100, this must be 50. This one's counting by tens. So if I were to write out the value of 10,000.000, we're counting by tens. We are going to know that value for sure. Our ones place is the estimated digit. Okay, so we know that it's 300 for sure. We know that it's 310 for sure. And then again, that 4 is the estimated digit. All right, and then the last ruler on the bottom here. If this is 1, we know that this is 0.5. So this is counting by 0.1. So again, if I write out my value of 10,000, oopsie, again, that should be a decimal. The value that I'm counting by is the tenths place, so I'm estimating my hundredths place. I should have 2 decimal places in my measurement, which we do. All right, so and again, that 3 is the estimated digit. All right, so the same values or the same ideas for recording the correct number of sig figs holds true for when you're making measurements with graduated cylinders or any other piece of equipment. So we've just been looking at rulers because it's easier to explain that way, but now we're going to take a look at our at graduated cylinders. So I'm just going to go ahead and write the number 10,000 at the top and just kind of reuse it for each one of these examples. All right, if I look at the first graduated cylinder, it's counting up every single time by 100. So I know my 100ths place, or hundreds place. I'm going to be estimating the tenths place. Tens, sorry, not tenths. So the 2, we know for sure. This 7 is our estimated digit, and then this is our placeholder 0. All right, so the one thing to remember, and we did talk about it when you guys were doing your lab, is to take the measurements of liquids at the bottom part of the meniscus. Okay, so at this bottom section of like where the liquid kind of curves or bends. All right, so again, we know that it was 200 for sure. This 7 is our estimated digit. So I'm gonna just underline the estimated digit. All right, in this graduated cylinder, if we take a look at what it's counting by, all right, if this is 10, we know this is 5, it's counting by ones. So if I go take a look at 10,000, I know this value for sure because it counts by ones. I should estimate my tenths place. So all of my measurements, if I had a graduated cylinder that looked like this, should have 1 decimal place. All right, so again, we're gonna go to the bottom part of the meniscus, kind of, right, and that's where I'm going to be making my measurement. So again, we know that this is 35, 36, and I should have an estimated digit. So maybe like 36.4, 36.5. Here they wrote 36.8. That's fine. Again, underlined number is the estimated digit. All right, last graduated cylinder, it's exactly similar to the one that we just talked about. So we know our ones place, and we're going to estimate our tenths place. All right, so again, bottom of the meniscus here. This is 10, 11, 12, 13. It looks like it's directly on the line. So notice how they wrote 13, but this 0.0, again, that 0 is that estimated digit. All right, so hopefully that helps you guys understand a little bit better about how measurements should look and how many sig figs a measurement should have. We'll get a little bit more practice with this on Tuesday. I guess good luck studying for your test. Remember, your test is either Tuesday or, Wednesday or Thursday, not Tuesday.